Could I ask somebody to close the door at the back? There's a bit of noise out there. Maybe lock it this time. Well, moving on to the second talk. Professor Sims has already had his drinks over lunch, so he's going to wait till the banquet. Delighted to introduce our second speaker, Professor Chris Sims. Fairly recent photograph in this case. Chris has had, as you will all know, different levels of detail, since we have a very interesting mix of statistics, business, econometrics, finance. He's had a profound impact on many areas of economics and public policy through his own work and research in econometrics, macroeconomics, macroeconomic theory, and policy-oriented studies. Most of us will be aware of some of his mainstream statistical econometric work in time series, sectoral regressions, and so forth, in the context of macroeconomic policy studies. And he's been really, in economics, central and flag-carrying in bringing Bayesian thinking, as well as Bayesian methodology, into economics. Chris is a teacher. He's a career teacher. And as Adrian, Chris has had a profound impact on the profession through advising the PhD students. And this is not only in economics, but also into statistics. Unlike the case of Adrian, I couldn't trace down the number of PhD students, but I have it on reliable authority from one of his colleagues, Mark Watson at Princeton. Chris has advised, quote, hordes of graduate students. Chris was at the University of Minnesota from the late 60s for about 23 years, and about a decade at Yale. And he's been at Princeton for about 14 or 15 years now. He's involved in a broad range of advisory and professional activities, national and international monetary and government agencies. He served as past president of the Econometric Society, and recently in 2012 of the American Economic Association. Among the very many awards and honors he's received for his work, he was elected to the National Academy of Sciences in 1989, and you all know he won the Nobel Prize with Dan Sargent in 2011. There's no Nobel Prize for statistics. A couple of recent Nobel laureates in economics, of course, were very heavily involved in statistics. And Chris's Nobel lecture was titled Statistical Modeling of Monetary Policy and its Effects. And Bayesian thinking was front and center from the start of the abstract. So if you haven't already read that lecture, then read it. And if you don't want to follow my direction to read it, I predict that when you've seen this talk today, you'll probably read it. Chris also teaches introductory statistics at Princeton. We had a little sidebar conversation about teaching statistics yesterday. And I visited his website. Probably for some of the statisticians, this could be an interesting Google for you. You'll be surprised at the range and the depth of statistical thinking, Bayesian thinking, and the teaching materials he has there. Foundational issues as well as modeling issues coming out of econometric applications. I believe his talk is linked to this. He's got a fairly provocative title in the talk today. So I'll invite him up here now. Delighted to present Professor Christopher Sims. I'll go around and flip the... you going to stand in front? PowerPoint?
It's a PowerPoint. No. Okay. All right. I'm happy to be here. This is an interesting audience to talk to. In fact, let me start by saying a little bit about what this talk grew out of. In 2007, I gave a talk at Duke to the Econometric Society summer meetings, whose subtitle was, Why Econometrics Should Always and Everywhere Be Bayesian. I didn't think that talk would be so much fun to present to this audience. For econometricians, it's still fun to present that kind of talk. I was thinking with Adrian's discussion of feeling of oppression that in econometrics, the Bayesian wave has not yet swept over the profession at all, particularly if you do time series econometrics and try to proceed as if you really don't care whether there are unit roots or not. I do that all the time, but my students then have trouble with it. So then in 2009, I prepared a critical comment that appeared in the Journal of Economic Perspectives on a paper by Angrist and Pischke titled "The Credibility Revolution in Empirical Economics: How Better Research Design is Taking the Con Out of Econometrics." This is a profoundly anti-Bayesian paper. It reflects their book, which is called Mostly Harmless Econometrics. And I'm going to talk some more about that. I developed the ideas there in more detail in a paper that's on my website, called Understanding Non-Bayesians. It's a chapter that was not published by Oxford University Press because I wouldn't sign their restrictive pre-publication agreement. I urge you all to try to have if you've got tenure, don't sign those contracts. This said I could not post a preprint of the paper on my website. Everybody else contributing to the volume signed it and posted their preprints, and Oxford never does anything about it, but I wouldn't sign. We should all be taking more principled stands on copyright. A subtitle for this talk, which goes a little bit beyond what's in these previous talks, might be "Why There Are No Real Bayesians." So I'm hoping that this will be as controversial here as why econometrics should always and everywhere be Bayesian was for the econometricians. So the outline of the talk is I'm going to try to point out what you probably all know. Bayesian decision theory is not descriptive of real-world decision-making. I'll also argue what you might not agree with. It's not even normative. And then suggest there's not really something obvious and better out there, and then ask, can we rescue it? So for the first question, is it descriptive of how people actually behave? There are fewer than two, probably no, Bayesian chess players. We know the optimal form of the decision rule. It's quite simple. For when two such players play each other, either white resigns, black resigns, or they agree on a draw all before the first move. And this is because, well, actually, we know the form of the rule, and it's very simple. We just haven't quite finished computing it yet. Bayesian decision theory pays no attention to costs of computation or to the possibility that we can be uncertain about something just because we don't know how to perform a calculation in the available time. And that kind of uncertainty is actually quite common in real-world decision-making. And there is a question, do we want to say, well, we shouldn't apply probabilities in that case, or should we be willing to apply probabilities to uncertain outcomes that we're uncertain about just because we don't know how to do a calculation? Is that right?
Just turning it up a bit, Chris.
Yeah, I know. I don't want to overwhelm people. So, all right. Okay. Okay. Is this a good volume? All right. But maybe we could say that Bayesian decision theory is approximately descriptive of the way people actually behave. This is what rational expectations economists did at the start. They said there was an objection. People don't actually compute optimal expected values of things. But the answer would be, well, they do it approximately, especially if they can repeat their behavior over and over again. They're going to arrive at a decision rule that is as if they were doing optimal forecasts. But natural selection does not select for Bayesian behavior. When a herd of gnus has to decide where to cross a river, there can be life or death consequences. This is a herd of gnus that chose the wrong place to cross the river. There were trees on the other side, and none of them could climb up. Natural selection does not want the gnus each to weigh the probability of death at each crossing point and choose the safest place to cross. That would have them all choosing the same place, and with some probability of suffering massive loss of life. Nature will select for probability matching behavior instead. That is, individuals should randomize over crossing points, choosing them with probability proportional to the probability of survival. This maximizes the expected future population of gnus. In fact, in some experimental settings, pigeons, rats, and people all do probability matching instead of Bayesian optimal behavior. If you give people two sources of candy or some reward, one rewards them half the time when they push the button, and one rewards them a quarter of the time. They don't, after a while, always choose the half-time button. They choose the two in about ratio 2 to 1. So if we're bred not to behave as Bayesians, perhaps it's too much to expect that the theory of optimal decision-making is going to be a good approximation to describing the way people actually behave in making decisions under uncertainty. Now, of course, this is a little oversimplified. You can see that this depends on the idea that there's an aggregate risk and individual choices being made. If you switch it around so that it's individual, independent risks, you get a different answer. But there's a discussion of this kind of issue in this paper that I think is quite interesting by Andy Lowe and Thomas Brennan, called The Origin of Behavior. You might look that up. Well, maybe we could say that Bayesian decision theory is descriptive of people trained in probability. This might even explain why Bayesians are still a minority. Truly Bayesian behavior limits reproductive success. We often use data that have been pre-processed by non-probabilistic methods to hide complexity. Macroeconomists use ad infinitum, the national income accounts. Microeconomists use data on individual consumption and saving, which are aggregates of monetary values. We use data from investment and employment, often on firms, and often these are seasonally adjusted. Financial economists use daily or monthly averages more often than actual tick data on transactions. Though there is, of course, a lot of recent interest in modeling tick data. It's really hard. It's very complex. And we don't have widely accepted and manageable theories of behavior of financial markets at the tick level. Whereas if we aggregate a little bit and talk about day-to-day behavior, Wiener processes, diffusion processes, that sort of thing start looking like not such a bad approximation. They're terrible approximations to minute-by-minute data. We simplify state spaces. A true Bayesian individual has only one decision problem to solve, and she's actually already solved it. There is no problem of what to have for breakfast on December 17th, 2013. She had to solve that problem for every possible condition. How hungry is she? What's available at the breakfast table? Have the Greeks seceded from the EMU, etc. Yesterday, as part of the decision problem of what to eat at the reception, December 16th. That is, decision problems are linked. And it's very hard in principle to argue that our practice of taking applied decision problems and breaking them out and having a state space and discussing how to solve this, and not at the same time thinking about other parallel related decision problems. We do that all the time, but in principle, there's really only one big decision problem that involves the state of the entire world. And of course, we can't solve that. There is a nice little paper by Savage about this issue of how you split up define the state space and how you justify breaking state spaces and probability distributions into pieces. And not so much about how you justify it, but it's about how you can't really justify it and how we have to proceed anyway. Here's an example of the way state spaces get simplified in real-world decision problems. It's interesting and not an accident that the place in econometrics where Bayesian methods using modern Markov chain Monte Carlo methods first broke in a big way is in macroeconomics in central banks, which have big staffs of people, many of whom have been trained in statistics. And they actually are taking probability models and trying to connect them to real-world decision problems in real time. So once it became clear that you could form posterior distributions over model parameters and hence over forecasts and predictions about the effects of policy actions, that this was actually a practical possibility. This kind of modeling based on Bayesian estimation spread very quickly through central banks around the world. Now, at the end of the 90s, there had been a string, this was before this Bayesian revolution in the central bank modeling. At the end of the 90s, there had been a string of high productivity growth quarters. There was low unemployment. One view was that low unemployment implied accelerated inflation would soon emerge, and that monetary policy should therefore be contractionary. Another view was that the high productivity growth, if sustained, would prevent inflation from emerging, so that no monetary contraction was appropriate. But was there reason to believe the high productivity growth was going to persist? At this time, or shortly after this, when people could talk about this period, I visited several central banks to discuss how econometric models were being used in the policy process. And at the Federal Reserve, I discussed exactly this episode. It came up spontaneously. Alan Greenspan does know Bayesian decision theory, and if you look at his speeches, remarkably often he uses the language of Bayesian decision theory to discuss how monetary policy is made and how uncertainty enters the policymaking process. Inside the Fed, people were talking about this issue in roughly decision theoretic terms, but they were framing it as the question of whether there has been a permanent change in the rate of growth of productivity. People discussed it as if it were a binary variable. There's been a shift or there hasn't. And in fact, I heard some economists at the Fed at the time explain, they were trying to be helpful to me. I was trying to find out how econometrics entered the policymaking process. And this was given as an example of the kind of time when econometrics really couldn't help. And why? It's because if they had taken a truly econometric approach to this issue, they would have had to test the null hypothesis of no change. And they could see that in this situation, where there were people who thought one way, people who thought the other, there was going to be some odds on the two propositions, that there had been a permanent change or not, that's what was relevant to decision making. And testing a null hypothesis was not helping you decide what the evidence said about the odds on this hypothesis. But the point I'm making here is that, of course, this wasn't a binary variable. Productivity growth is a complicated dynamic process, and what you, in principle, really ought to have been doing is trying to model that process and the joint behavior of that process with a bunch of other measurable macroeconomic variables and produce a conclusion about the range of uncertainty about how persistent it might be and so on, and map that into discussions of what the policy should be. But that was way too complicated for people to do in the real-time decision-making context at the time. An actual Bayesian analysis by self-proclaimed Bayesian statistician does not use real priors or realistically complex models. We use Gaussian distributions, gamma distributions, beta distributions, binomial, multinomial, Dirichlet, Wishart, We have this basket of distributions. But in a real model with a state space with, say, 10 dimensions, if you actually started to try to query people and ask them about how likely is this region of the state space relative to that, it's pretty unlikely that you'd come up with anything that easily is summarized by one of these toolbox distributions. And once you got away from the toolbox distributions and started trying to elicit a prior over a 10-dimensional space, region by region, you might spend the rest of your academic career eliciting a prior. Economists at central banks are using Bayesian methods on models with 30-dimensional or 150-dimensional parameter spaces. They use the Bayesian methods with priors. The priors are determined as much by tractability as by careful assessment of anyone's prior beliefs. We also see what I call recurrent heresies, and here are examples in economics. In macroeconomics, there is a school that's highly influential of macroeconomics that was originally called the real business cycle school. It's no longer restricted to analysis of real business cycles, but it is quantitative. It uses probability models to generate artificial time series and compute predicted statistics. But in most of its branches, this school is overtly hostile to any form of probabilistic inference. Their argument is that models should be adapted to their purpose, that models that are adapted to a particular purpose, though one criticism of them is that it's not exactly clear what purpose they have in mind. They aren't very precise about that. They seem to reduce it to the purpose being to match a small number of moments of the data. But the idea is that a model should be adapted to its purpose. Different models are good for different purposes. And a model that's adapted to a purpose and doesn't aim at a complete probability model of the whole system of data that's available will be rejected by formal inference methods, because the formal inference methods will confront the model with some messy, complicated model that fits better. So what? It's not a very nice model. It's not very useful. They don't like they would reject. Formal statistics would reject the models they use, and they're not interested in those rejections. Another heresy whose advocates would not see themselves as in any way aligned to the real business cycle school is the Anderson-Pischke credibility revolution in econometrics. It is framed mostly as an argument for using robust inferential methods. But much of its appeal, in my view, is that it argues for using without apology simple models. Ordinary least squares estimates of best linear predictors, linear instrumental variables of LATE, local average treatment effects. The idea is that the idea behind this, where credibility comes in, is that if we promise to stick with a very simple model like this, no matter how big the sample size gets, the asymptotics will take over. If you're estimating a 2-parameter least squares regression and you have 350,000 observations, the asymptotic theory is going to be very good in almost any application, unless you have some very strange x's. So the idea is we should try to avoid having to think about whether the residuals are normal or not, whether this might be a nonlinear relationship, whether there might be other kinds, even whether we should think about whether there's conditional heteroscedasticity. The argument here for OLS is you should use OLS with sandwich covariance matrices. That is, you use ordinary least squares, and then you use an estimate of the covariance matrix, the asymptotic covariance matrix for ordinary least squares, which is robust against conditional heteroscedasticity. But what's implicit here is that my view is that if you found that the sandwich estimator of the variances of your coefficients is very different from what you get from sigma squared x prime x inverse, that means there's something going on in the data that you haven't modeled, and it's maybe very important. It's related to the idea that achieving robustness and inference by limiting efficiency is not good practice. In many examples of application, the conclusion comes, one important kind of conclusion is there's no significant relationship. If you're using inefficient methods and concluding that that a relationship is insignificant, you can be very much distorting the implications of the data. So this view, which is very influential now amongst especially labor economists, people who deal with large cross-section data sets, is that we should not be trying to look at fancy models, not be trying to model all the complicated behavior in the data set. We should be sticking to a simple model. Implicit is the idea that maybe for our purposes, all that matters is the linear regression coefficient. But in any application, you can easily, people will be looking at questions like, and Angus and Pischke talked about this at great length, this example of what is the effect of class size on student learning. There have been actual controlled experiments on what happens to student achievement with class size changes. You can use OLS or instrumental variables to get an estimate of the best linear fit to this relationship. But if you really think about, you're a principal in a school. Most schools in the US have huge variation in class size already. There are advanced placement, pre-calculus, and ancient history courses with 40 students. They're all college-bound, very well behaved. And there are 7 students classes for people who are developmentally delayed or behavior problems. And then there's variation in between. The principal has some reason for creating this variation. There's some idea that things go better if you have very small class sizes for people with behavior problems, and not much loss for the well-behaved students. But this linear regression coefficient doesn't tell you anything about what to do about whether to change your distribution of class sizes. It doesn't tell you if you're told reduce average class sizes, should you do it by compressing the distribution of class sizes, or should you do it by just taking the same distribution and proportionately reducing all the class sizes. So that's my argument with this and why I call it a heresy. And it's unfortunate because what it does is tell graduate students in economics, all this complicated nonlinear modeling, generalized least squares, random effects, you don't really have to worry about that. You learn about least squares and the sandwich estimate of the covariance matrix, linear instrumental variables and the sandwich estimate of the covariance matrix. So that's all you really need. And I think the appeal of this is a lot like the appeal of the real business cycle theory. It tells people you can use simple, understandable models, and it legitimizes that, and legitimizes resistance to nitpicky criticism from econometricians and statisticians. So is there a principled response to this situation? I should say, unfortunately, I don't really have a good answer. I'm just going to make some remarks. We should recognize that Bayesian decision theory is only approximately descriptive and only for a limited range of behavior. So this is really more for economists. The rational expectations model of behavior, of course, both in finance and economics, there's a lot of interest recently in behavioral economics, looking for regularities in the way people's behavior differs from this rational expectations paradigm. But the rational expectations paradigm has been very successful, and I'm not arguing that we should throw it out, but just recognize that we should expect there to be systematic deviations from its predictions about behavior of individual agents in the economy. And we should also recognize that simplicity of a model can be more important than we usually acknowledge. And for this, I think it's useful to think about data compression. Rissanen, many of you probably know that Rissanen pointed out that one can arrive at something close to likelihood-based inference by considering the problem of compressing a data set. If you have a data set consisting of real numbers to, say, 10 significant digits, and they're serially correlated, you can replace that data set by, say, a first or second order autoregressive model plus a list of the residuals to many fewer significant digits, and maybe the initial value to the same number of significant digits, and get the same accuracy with a much smaller data file. And it turns out that this way of thinking about what's a good probability model is very close to exactly what you get by thinking about a probability model and fitting it to the data set by likelihood methods. You record a model and its residuals or shocks and economize on storage. And like Bayesian inference, this approach penalizes model complexity, since a more complex model requires more storage space. But Rissanen was thinking about lossless compression. His approach leads to comparing models based on likelihood with a model complexity penalty. Much, in fact, probably most of the data compression that's everywhere today is lossy. I say consider image and sound storage formats. I guess I only mentioned image because I couldn't remember the names of the sound ones. But for images, there's a format called TIFF that's used by professional photographers and a few other places, which is lossless. It compresses graphics, but in a way that preserves the full detail in an original bit scan. But more commonly used for photos on the web is JPEG, which is lossy. And actually, you can, in many programs, you can control how lossy it is by picking intensity for the compression. Now, if we think about TIFF and JPEG from the perspective of Rissanen's way of thinking about probabilities and probability models, TIFF is a candidate probability model where the criterion is like likelihood. You're trying to, if somebody can come along and on your data set say, well, you compress this by TIFF and this is the size of sample you get, I can actually tell you a model for this data that lets you compress it more, even including the description of the probability model. Then you'd say that model is better than TIFF. Both are going to produce the same thing in the end. They're going to give you a lossless compression. You can reinflate the data and get back the original file. JPEG throws away information. In particular, if you looked at blown up JPEG images, you know that areas that are all nearly the same color and shades just get all made the same. And for photos, this is a very good idea. When people look at photos that have been compressed by JPEG, they can often, especially if it's going to be shown at the resolution on the internet, they can often not tell the difference between the compressed and the uncompressed file, even though it's not possible to go back to the original from the JPEG file. So for a given data set, evaluating lossless compression amounts to likelihood-based comparison of models when one of the models you're comparing is correct. Just to make this more precise, suppose we have one model that gives P1 to an event or to a kind of entry in the data file, and another gives the probability P2, with the ratio P1 over P2 very large. Optimal compression depends on probabilities of various kinds of entries in the file, and if that ratio is very big, the ratio has a big impact of compression, even if P1 and P2 are both very small. When this rare event that has low probability under both models occurs, the P2 model will use much more storage for it than the P1 model, even though both will use a lot of storage because it's a rare event. But suppose we don't really care about accurately recovering rare data points of this type. We have the option of just saying, I'm just going to ignore or not try to reproduce accurately. My lossy compression is just going to lose this kind of low probability event. Now, whether that's important or not depends on what the low probability event is. If the low probability event is a certain pattern of alternation of colors in a snapshot, it may well be that this kind of pattern is both rare and ignoring it and replacing it with some arbitrary replacement does almost no violence to individuals' appreciation of the compressed photograph. And in that case, lossy compression would give you a very different answer. Notice that this emphasis on what likelihood-based inference does is look for where the models have the biggest ratio of predicted probabilities and focus on them in deciding which model is right. But there's nothing, that's the Kullback-Leibler distance measure. There's nothing that says that that distance measure is necessarily what's interesting to us in a particular application. So with lossy compression, we're sure we're going to lose information. So how do we decide whether a lossy compression method is good or not? Professional photographers do not keep their work stored in JPEG format because they know they may need to vignette it, enlarge it, change it. It may turn out that a small part of the whole image is important to them. And so their loss function is not just can the average internet browser user tell the difference between the original and TIFF. It's much more complicated than that. A black and white version of the image may be all that's needed for some purposes and can be many times smaller. JPEG, as I've already said, suppresses detail in large areas of similar color and shade. And whether we care about this depends on what images are being compressed and what the compressed file is going to be used for. So are there lessons for this in statistics? An ideal approach that we may sometimes approximate and that I think we should be teaching our students is the right way to proceed is that we should be attempting to find a true model, exploring increasingly complex models in increasingly large and informative samples. Now that doesn't mean that we think that we necessarily are going to find a true model. Think about this lossless compression. It's not necessarily true that there is an optimal way to do the compression. What's important to us, the reason we're willing to use compression by itself as the criterion is that we know that we're doing a lossless compression exercise, and we're really interested in shrinking the model, and there's going to be no losses. So it doesn't matter what uses are going to be this thing is going to be put to. So in statistics, you can say, well, I don't know whether any of these models are true. But if we think that the model collection we're looking at includes the best we can do with this data set and our resources, and we're willing to admit that if somebody comes along and shows using likelihood-based methods that the posterior odds using any reasonable prior on this new model strongly favor the new model over any of the old models, we move right to the new model. Then we're in the business of effectively looking for a true model. Then likelihood-based measures of fit are right. But we're not necessarily in that position. We have to recognize that in some cases, lossy models will be useful to people. These are models that are deliberately inaccurate. people who are using them know that they don't actually capture all the detail in the probability distribution for the data. But they are simpler in some relevant sense. And exactly what sense is relevant is a hard question here, because we're now out of the realm of saying we can measure the size of the model by data compression. There may be other dimensions to what makes a model comfortable for people or useful for people. So how do we evaluate them? We have to recognize that the simplicity of the model and the data to which it will be applied and the use to which the model will be put will all be relevant. That is, it's not just a question of, is there some other model that we can show fits better? An ideal case, which was considered by Frank Schorfheide of Penn in his thesis and a subsequent paper that came out of his thesis, is one where we have a candidate true model available. i.e. one we don't see how to beat on likelihood-based measures of fit. Schorfheide calls this a Bayes model. If you have such a model available, then you can evaluate simpler models by asking how would they behave in their intended use with the Bayes model as treated as generating the data. And I think that for cases like that, Schorfheide's setup is exactly right. But we have to recognize that this is not always possible. We're often confronted with a collection of models to evaluate, or a model with a parameter space to evaluate, where we know that given enough time and using the right methods, we could construct a better fitting model, but we have to work with what we have. Nobody's given us an estimate of such a better fitting model. Is there anything we can do? I think there's no detailed formalism for this. We have to recognize that there's no way to evaluate such models without considering what the model will be used for and what the true model might in fact be, even if we don't have an example in front of us. Such models also often arise in the form not of an actual elaborated model, but a decision rule or data summary that's not probabilistic. In that case, we can try to formulate a probability model that would make the procedure non-lossy. In other words, we can ask, if you were going to do this, if you're going to use OLS and the sandwich, what would your probability model have to be to tell you that's the right thing to do, the best thing to do? That can help us understand what range of true models might make the distortions of the simple model unimportant for the model's application. So that brings me to the end, unfortunately, of what I have to say in a positive way. The positive conclusions may seem anticlimactic, unoriginal, and commonsensical. Here's a summary of them in two main points. Principled statisticians and econometricians should recognize that a model dominated in fit by another model can nonetheless be useful, and we should not just throw up our hands and walk away when we're confronted with such a model. We should try to provide informed criticism and evaluation of such models. Users of practical models for real decisions, like real business cyclists, should recognize that there can be value in talking with econometricians and statisticians that might threaten to show their models to be false. So long as the econometricians and statisticians don't simply thumb their noses at the people using the models and saying, see, I've shown your model is false, we can instead help users of the models to understand what assumptions about the range of possible true models and about the range of applications of the model can actually justify the model and could guide model improvement, and to do this without insisting that only true models are interesting.
Thank you, Chris. And thank you for press forwarding. We're back on schedule. Time for some questions or comments or addenda. Questions for Chris?
Too obvious.
Well, there's an element of that. There's an element of preaching to the choir, certainly from a one-statistician's perspective.
Somebody have
Question from the back.
Just a comment. John Suzuki once said that better an approximate model for a real problem than a great model for a non-problem. Now, it seems to me that there's a little bit of that in your talk.
Yeah, that's, though I'm trying to emphasize that we shouldn't let people get away with saying, well, I know I will have to use an approximate model, and I don't care that you can show there's something wrong with my model, that I could fit better. People using we should be trying to convince people who use approximate models that understanding the directions in which their model doesn't fit is important, because they need to be able to evaluate whether the lack of fit in that dimension of behavior of the data is important to the use they're going to make of the model or not. If you look at the DSGE models in use in central banks, they've been constructed to qualitatively match the more densely parameterized structural vector order regressions that somewhat preceded them in terms of the way they imply monetary policy affects the economy. But the DSGEs are low-order models. They have, if you look at their impulse responses, they're very smooth, and they tend not to oscillate in sign more than once. If you look at the estimates from the structural VIRs, which are more densely parameterized, it's pretty clear that they aren't just simple linear combinations of a couple of exponentials. They can behave in a much richer way. People ought to understand that and be willing to make an argument that it doesn't matter whether the impulse response is as smooth as is implied in the DSGE. Actually, in some cases, there are whole sections of the impulse responses that have the wrong sign relative to structural vector order regression. And that requires an even stronger argument. There's a tendency for people who are using these approximate models to say, I don't care. And what I'm trying to do is suggest that there's room for interaction and discussion between people who know how to and are interested in more complex models of joint probability distributions to talk to people who are using simpler models knowing that they don't fit.
Chris, I suppose everybody could think of principles you could add, such as even a simple model could be misleading. But I wanted to point out a historical background in economic statistics to some of what you're talking about, which I'm thinking of associating with you and rephrasing it in your terms as to how lossy compression can yield greater information and understanding. And the scientist I have in mind is William Stanley Jevons and his work on index numbers in the 1860s and thereabouts, where he had to hold the ground against a huge amount of criticism, which said that you can't do that. You cannot average pig iron and pepper, for example. And in his defense, which I can't quite quote as elegantly as he launched it, was that if it were necessary to explain every possible deviation and every one of the numbers that was involved, the whole of social science would come grinding to a halt. That the idea of throwing data away, in effect, by compressing with loss, actually led to greater understanding, was a major advance in statistical science.
Well, I qualify that by saying another thing that's going on in economics is people fitting dynamic factor models, where essentially they're trying to go back and ask, could we, if we explicitly did probability modeling of aggregation and indexation, could we do a better job than what people do with intuitive weighting schemes? And I think there's room for I'm not a big fan of these dynamic factor models used that way, but I think there is room for interaction. It is a little puzzling and disturbing that there's so little questioning of whether there is any principle behind the aggregation that we use all the time. There was a commission on price indexes some years back that Angus Deaton and others worked on, but it doesn't happen very often. And that was just the price index, industrial production index. There's no academic discussion of that. There's plenty of academic discussion about optimal seasonal adjustment, but it still gets done the same old way. So we should be aware, and I hope always a little bit uneasy about that.
Yeah.
Yeah, so I'm trying to wrap my head around your talk because I sort of think you can justify the Anger's approach based on the news or something. In a lot of the social science people that I deal with, the two-parameter regression model is one small piece of a much larger problem, and they're really busy. So is it, if that's the case, they probably shouldn't be optimal Bayesian decision makers. They should do the thing that's quick and easy and get on with their lives, because finding the true model is going to be hard. Is that right?
I agree. That's why people want to use simple models. But I also say we ought to be trying to make sure they understand what can go wrong with doing that. Like, the only way to say that OLS plus sandwich is not even asymptotically inefficient is to say you actually believe there is nonlinearity, but you don't care. If it's actually true that the conditional expectation of y given x is x beta, then you can get better efficiency than estimating by OLS, and you should be trying to do it unless that's not really relevant to the use you're making of the data. Are you estimating the two-equation regression and saying, see, the coefficient on class time is insignificant, so let's go on to some other policy measure? If that's what you're doing, there's a real danger in just using OLS and not recognizing that nonlinearity is either there or not, and you might need to figure that out. GLS might give you more efficient estimates, and that might affect your conclusions. So the gist of my talk is it's not surprising that a lot of people in social science who are hitting the stata button for OLS with clustered standard errors and not asking any questions. But we should be training them to ask, so they know how to ask the questions and that there are questions to be asked.
Why can you not address this, at least in part, by including the cost of computation in the decision process itself, by modeling the modeling?
Well, there's one level which says, of course, there's a circularity there. But I agree, let's forget about that. We can think about having some time at the beginning where computation is free and we can model computation costs. Yes, I agree with that, and it's not just computation. I have actually a branch of the research I do bringing information theoretic constraints on processing information into optimal decision making. And I think the costs of computation, I think, are a little harder to model. But in both cases, there's an issue of, they're very hard issues. Like in Rasanen's approach, you're thinking about embedding the model in the file. Well, suppose there's a question of, suppose you're going to have lots of files like this. Each one might optimally have different coefficients in the autoregressive model. But maybe it would be better just to pick an average set of coefficients, and then you don't have to put it in the file. Everybody knows that it's in a reference file. So then you get a different criterion. I think with computational costs, there can be the same issue. The cost of solving a problem that's very similar to one you've solved before may be small, even though it was big on the one you solved before. So I think they're very hard issues there. But I agree with you that you can do that. You can also put probabilities. I mean, in computer chess, they put effectively probabilities of winning from various positions into their algorithm. It's kind of a Bayesian algorithm in a way. But of course, there isn't the probability of winning if you really could calculate
0 or 1.
Yeah, 0 or 1, if you could really do the calculation. So it's, but you can see that in computer chess, you can say, you can put a cost on how many steps ahead you have to go and how fast you can do that. And the complexity of the range of position weights you consider is going to be sensitive to that. So that's all happening in computer chess. And you can imagine, in principle, doing it in other areas too. But it's not just cost of computation, because here we're not just talking about, you've got to put in cost of computations, but then there's on the other side, what are you going to use this for? You're going to lose something. There are different kinds, you can lose different kinds of details with different kinds of models. How do you assess what kinds of losses of detail matter?
One last question?
Yeah, okay,
George.
Chris, turn back to your real business cycle example. You see users of real business cycle models as ultimately, if one looks carefully as the econometrician from the outside, they're maneuvering around those so-called structural models to try and match this list of sample models. They're not really getting it from external data sets, as they say. So in effect, what they're doing is a lousy method of, they're using a lousy optimizer for method of moments. And so it becomes hard for the econometrician not to sneer at that. At the same time, to have a useful discussion seems impossible because the calibrationists have built this wall up around their methodology, and digging around in their models and trying to find out where the dead bodies are is not rewarding professionally, I don't think. And they already know where the dead bodies are, I think, but won't tell us. So do you have any thoughts on how to change the situation in the context of
I think you're a little more pessimistic about this than I am. It all depends on which RBC guys you've been talking to recently, I think. But you see examples of people who do calibration first and then try to move on to doing a formal fit. I just saw, I think it was at a workshop recently at Princeton where somebody was saying, well, I can't fit this whole model, so I'm fixing these 5 parameters, and these 5 parameters I'm going to use simulated method of moments and put standard errors on. Of course, that's a kind of a crude compromise, but it's a step towards creating communication. And you also see occasionally people from RBC school actually computing impulse responses. It's one of the annoying mysteries that impulse responses have become associated with vector autoregressions. And so people, true believers in the RBC methodology, never do it. They compute and display pages of autocovariance functions and cross-autocovariance functions, which are much less informative. And it's because somehow there's a taboo on impulse responses. So these kinds of things are hard to take and they're irrational. But you do see, I think, younger people who aren't infected with. At the beginning of the RBC stuff, they were solving probabilistic dynamic programming problems with multiple agents doing dynamic programming. It was a big computer challenge, and they didn't want to do all their work, get simulations that sort of matched some of the data, were kind of interesting, and then be told, your model doesn't fit. So they got very testy. it's no longer, you can no longer justify not trying to fit models just because it takes so long to solve them. They don't take long to solve anymore. So I think that's actually producing change amongst the younger people in these areas.
Well, I think we'll pull the session to a close. Let's thank Chris one more time.